Venn diagrams, like other topics within the field of probability or statistics, is a means of representing data from which we can work out potentially probabilities. These, as you may know, are represented using circles that may be overlapping with each other, or they could be completely separate if the given scenario meant that one thing could not happen at the same time as the next. Within these circles, we can then have different notations to represent which parts of the diagram are being represented. For instance, if we wanted to represent just this bit here, which is in the overlap, we could do this by saying it is A intersection B, this arch shape, this N shape representing intersection. However, if we wish to represent everything within either circle, then that would be A union B. So it's now a U shape in the middle. To be clear with union, because it can get a little bit tricky, this is saying the region that's going to be shaded just has to fit one of the criteria, not both. For instance, this bit here on the left, that is just within circle A. No part of that is within circle B, yet it's still counted because it fits that first criteria. And then the bit on the right that's just in B, again, that fits B, so even though it doesn't fit A, it's still marked. And same with the overlap, because that does fit both. Shade in what's on the left-hand side, then shading what's on the right-hand side, even if those two things may contradict each other slightly. It's just saying you have to fit one or the other, whereas the intersection is it has to be both simultaneously. Now, what if we wanted to completely ignore a given circle, though? What if we wanted to completely ignore A? Well, this in Venn diagrams is represented with an apostrophe. This apostrophe may be quite subtle on the printing of the paper, so you need to be on the lookout for it. But if it's there, what that's saying is, rather than shading in A, we'll shade in this bit here, that's only B. Again, it's not the intersection because that is in part of A. But also, that's then the outside of the circles, because that's still going to exist somewhere within a frame. Usually this will be within boxes, they don't have to be, but there can potentially be something outside the circles if something doesn't fit any given criteria. What may happen then within questions is you could be given a pre-existing Venn diagram and you're asked to list what numbers exist or what numbers fit the rule A intersection B or A union B, or maybe A union not B or something like that. It's just up to you then to, okay, this is what this notation means, this is the sections, these are the numbers. They can either just say there are 3 things existing in this circle, there are 10 things existing in this circle, just give it as a singular number representing the quantity in there. Maybe it's not to do with numbers at all, maybe the question is about fruit that's being eaten, or like, so some people eat this fruit, some people eat that fruit. Maybe the question's saying, okay, this circle is animals that have fur, and another circle is animals that have 4 legs. And we're saying we're not going to list every single animal that fits within each circle. We're going to say, okay, there are 4 animals here, and there are 5 animals here, and then there's this many in the intersection. Alternatively, they could spell everything out and say, okay, this goes here, this goes here, this goes here. This is all the stuff in circle A, and this is all the stuff in circle B. Quite often, these are in turn, again, numbers. So, when you're looking at a Venn diagram, you just have to be very careful from reading the question. The numbers inside the circle, are they individual things that exist in the circle, or is it just saying, this is how many of that thing there are? It's just a subtle difference. And when it then comes to asking you in the question, like maybe it says, how many things are in circle A? Are you counting multiple examples of numbers that are appearing inside this region? Or you just look at them as, okay, that says 3, that means there are 3 things. We're going to just try examples of both here, just so we're clear on the distinction. Perhaps we have, again, just these 2 circles overlapping, our A and our B. Now, this swirly symbol here, this is the Greek letter Xi. It refers to everything within the diagram, including the outside. So here, this is saying the Venn diagram as a whole contains all integers from 1 to 10, so integers being whole numbers. And then we're told, within circle A, there is a 1, a 3, a 4, and a 5. And then within set B or circle B, there's a 2, 3, 5, 6, and 9. Okay, well, let's just go through the integers from 1 to 10 and see where they fall. So 1, we're told that exists in circle A, but it's not listed in B. So 1 is just going to be here. 2, on the other hand, only exists in B. So 2 is going to go over here. 3 exists in both of these lists. So 3 is going to be in the overlap. 4 is only in A. 5 is in both. 6 is only in B. 7 doesn't appear in either list. So 7 we're going to put on the outside. Same with 8. 9 appears only in B. And then 10 goes on the outside as well. If the question then asked us, what is the probability of, if you pick a random number, it fitting the rule of A intersection B? Well, there are 2 numbers that exist in that intersection. That's 2 out of a total 10. So that's 2 over 10, or 1 over 5. If instead they had asked for A union B, then that would be saying, okay, anything in either A or B, there's 1, 2, 3, 4, 5, 6, 7, and again, that's out of 10. Right? Now, that was an example of if they just spelt out what everything inside of a given set was, or inside of the diagram was. What if, again, by contrast, they instead just said there are this many things here, there are this many things here? Just clearing up the space. So we might have that in the diagram as a whole, we're told there are 12 things, and this might be represented by maybe the question saying, okay, this circle is animals that have fur, and another circle is animals that have 4 legs. And we're saying we're not going to list every single animal that fits within each circle. We're going to say, okay, there are 4 animals here, and there are 5 animals here, and then there's this many in the intersection. Alternatively, they could spell everything out and say, okay, this goes here, this goes here, this goes here. This is all the stuff in circle A, and this is all the stuff in circle B. Quite often, these are, in turn, again, numbers. So, when you're looking at a Venn diagram, you just have to be very careful from reading the question. The numbers inside the circle, are they individual things that exist in the circle, or is it just saying, this is how many of that thing there are? It's just a subtle difference. And when it then comes to asking you in the question, like maybe it says, how many things are in circle A? Are you counting multiple examples of numbers that are appearing inside this region? Or are you just looking at them as, okay, that says 3, that means there are 3 things. We're going to just try examples of both here, just so we're clear on the distinction. Perhaps we have, again, just these 2 circles overlapping, our A and our B. Now, this swirly symbol here, this is the Greek letter Gcse. It refers to everything within the diagram, including the outside. So here, this is saying the Venn diagram as a whole contains all integers from 1 to 10, so integers being whole numbers. And then we're told, within circle A, there is a 1, a 3, a 4, and a 5. And then within set B, or circle B, there's... Now, before we actually move on to you having a go at these questions on your own, I'm actually going to give you one more example, just to show how we can use the different notations in relation to each other, as well as showing that these Venn diagrams can also work just entirely on probabilities. So rather than saying like what the whole Venn diagram contains, or what A contains, or what B contains, what we'll instead say is that the probability of getting an A, not A, union, not B, is 0.8. Now I'm just going to be switching colours up between each rule, just because I'm going to mark what each region represents in a second. The probability of getting B is 0.3, and the probability of getting not A in general is 0.5. Based on this then, what is the probability of getting A intersection not B? Well, as I say, it's just to show what represents what. If we're here doing not A union not B, because it's union, we'll just do one, then the other. The regions that represented not A is going to be this bit in here, and then the outside. And then not B, again, is going to be the outside, but then also this bit that's only A. So it's basically everywhere but the intersection. As for this, the probability of B, because there's no mention of A, this is the entire circle B. So that's both the intersection and this main bit here. Then for not A, again, that's basically what we label with this first green bit. So it's the B on its own and the outside, because the intersection is again part of A. And then lastly, what we're looking for, this A intersection not B, the bit of this diagram that is simultaneously within A and yet not within B, that's just this region here. Okay? Right. So how on earth are we going to work out this blue bit here? Well, as I say, if this here, this probability, is including every region but the intersection, we can actually use this to fill in the intersection first. Because these are probabilities, because they're all P bracket something, the probabilities have to add up to 1 in total. That's in any kind of probability. 1 has to be the total, 1 is a certainty. So if all of this is 0.8, 1 minus 0.8 is going to equal 0.2. And that has to be the probability, say, of the intersection. So 0.2 is going to go in here. Next, if the probability of B in its entirety is 0.3, and we've used up 0.2 here, that only leaves a 0.1 probability of getting just B on its own. If not A is 0.5 in total, and that's these two regions, well, we've used up 0.1 here. That leaves us just with 0.4 for the outside. And now, because we can either say we know it all has to add up to 1, or we know all the green sections had to add up to 0.8. Either way, just by doing some subtraction, 1 minus 0.4 minus 0.2 minus 0.1, or 0.8 minus 0.4 minus 0.1, you end up with this here being a probability of 0.3, which would be the answer that we're looking for. Okay, so yes, Venn diagrams can get a little bit complicated when you're bringing in knots and unions and intersections. We'll just need to keep track of them. If we're alright with this for now, and again, it will come with practice, let's have a go at a question for you. Just clearing the space once more. What if, using again these same two sets as A and RB, we have that Gcse, the universe, the diagram in its entirety, contains all odd numbers between 0 and 30. A is then going to contain 3, 9, 15, 21, and 27. Then B is going to contain 5, 15, and 25. So again, just to repeat, our universe is all odd numbers from 1 to 30, or 0 to 30. A is 3, 9, 15, 21, and 27. And B is 5, 15, 25. First of all, fill in this diagram, therefore, to represent all of this information. And then secondly, can you find what is the probability of, if you were to pick a random number from this diagram, it fulfilling the criteria of A union B? Pause the video, have a go for yourself, and then press play again when you're ready to compare. Alright, so for filling in this diagram, first of all, if the universe, this Gcse, this diagram, is all odd numbers from 0 to 30, let's just start going through them and see which ones appear on the list. If they don't appear in either A or B, then they'll go on the outside. So 1, first of all, no, we haven't got that in either list, so 1 goes on the outside. 3, that's in A only, so go here. 5 is in B only. 7 is in neither. 9 is in A. 11 is in neither. 13 is in neither. 15 appears in both. 17 is in neither. 19 is in neither. 21 is in A. 23 is in neither. and 25 is in B, and then 27 is in A, and just to wrap up, 29, once again, is in neither. So that's where all of your numbers should have fallen. As then for working out the probability of being A union B, well, it's basically saying, out of how many numbers there are in total, first of all, how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which makes sense because that's half of 30. Half the numbers between 0 and 30 are going to be odd. So out of 15, how many of them are in either A or in B? Well, we have 1, 2, 3, 4, 5, 6, 7. So the probability of A union B is 7 out of 15. If we're happy with that, let's have a look at an actual paper question. Now, when you get to an actual paper, as it usually does when you get to the actual exams, they can tweak things slightly. For instance, here, this question, as we read through it, we will find has 3 variables. So we're going to end up with 3 overlapping circles. So just to do so, there were 50 people being asked if they speak French, German, or Spanish. Now, of these people, 31 of them speak French, 2 speak French, German, and Spanish, 4 speak French and Spanish, but not German, 7 speak German and Spanish, 8 do not speak any of the languages, and all 10 people who speak German speak at least one other language. Now, 2 of these 50 people are going to be chosen at random. Work out the probability that they only speak Spanish. Well, we have our 3 circles that we can draw out to represent this information. Just label them, so F for French, G for German, and S for Spanish. When going through a question like this, I would always suggest start in the centre, start where there's the most overlaps and build outwards. We'll see why in a second. If 2 people speak French, German, and Spanish, that's 2 people in the intersection of all 3. So you're going to have a 2 here. Now, 4 people speak French and Spanish, but not German. Well, French and Spanish, that's going to be this overlap here. They don't speak German, however, so we're not including this 2. So that 4 just goes in its entirety there. By contrast, however, 7 speak German and Spanish. So German and Spanish is this overlap here. However, that statement makes no reference to if they speak French or not. So we must assume that 7 contains this 2. That leaves only 5, therefore, to go in that little bit there. 8 do not speak any of the languages. Okay, well, that's 8 that's going to go on the outside. And then all 10 people who speak German speak at least one language. So there's actually no one who does just German. This bit here is 0. And, just to go back to top, because I'm aware I skipped over it, that 31 people speak French. Again, that's going to contain this entire circle because it makes no other reference to other languages. So we have this information. What can we do to start filling in any more of the blanks? Well, to actually go back to that last statement, it's all 10 people who speak German will speak another language. Then we know there are 10 people in total in this German circle. 2 and 5, making 7, have already been used up. And that leaves 3 to go here. Now we can turn back to that French statement. So if 31 people speak French in total, and we've used up 3 and 2 and 4, that being 9 in total. If you take 9 away from the 31, that leaves 22 people just speaking French. And from that, with all the rest of these numbers, we can finally work out what only Spanish is going to be. And that, obviously, you can see, is what we're trying to work out. So, just to add up all of the numbers we already have, so 22 add 3 is 25, add 2 is 27, add 4 is 31, because the whole French is 31, add 5 is 36, and add 8 is going to be 44. Obviously, add 0 doesn't make a difference. If that's 44 people, and we know there are 50 in total, that leaves 6 people being only Spanish. It asks those specifically for the probability. That has to be how many fit this criteria out of everyone. That's therefore 6 out of 50. We're not just after the probability of getting one student, though. We're after 2, with both of them only able to speak Spanish. This here is just probability of getting 1 student. To find the probability of the second, if there were 6 people who only take Spanish to start with and you've moved 1 away, there's only going to be 5 left. And if there were 50 people in total to start with and you've taken 1 away, there's only 49 left. It's therefore this multiplication that you're going to put into your calculator. And that's going to give you an overall probability of both of them only speaking Spanish of 3 over 245.